Good afternoon. Today I'm presenting my research on achieving better immune protection against pertussis infections. Pertussis is a globally endemic research infection, mainly affecting infants and children. In the past decade, there have been about 24 million cases worldwide, out of which 53% mortality was observed in infants less than 1 year old. There is a vaccine for acellular pertussis, given as a combination with diphtheria and tetanus. But this vaccine is proving inadequate in controlling the infections, especially in infants. This can be because, being intramuscularly injected, it fails to induce immunity in the nasal mucosa, which is the main site of infection. And also possibly, the immunity diminishes over time. Hence, there is a need to redesign the current acellular pertussis vaccine. So when we compare the immune responses generated by natural pertussis infections versus the current acellular vaccine, natural infections produce a more Th1 type of response, which is characterized by high IgG2A antibodies. And they also produce mucosal immunity with high IgA and nasal secretory SIgA antibodies. But the current vaccine actually leans towards a Th2 type of immune response, which is more greater towards high IgG1 antibodies. And hence, we need to redesign this vaccine such that there's a greater Th1 type of response to produce a balanced Th1 Th2 immunity. In this research, we hypothesize that formulation of pertussis antigens with vaccine adjuvants and cationic lipids as nanoparticles for intranasal delivery will help achieve good and enhanced immunity. We aim for better cellular immunity and Th1 response, characterized by high IgG2A antibodies. These are responsible for induction of long-term adaptive immunity. And we also wish to generate mucosal immunity with high serum IgA and nasal secretory SIgA antibodies. And so we set out this task by taking a triple adjuvant called the triage, which consists of a TLR agonist, poly-IC, a host defense peptide, IDR1002, in a polyphosphazine carrier. These triage, when combined together, helps to enhance the immunogenicity of these antigens. Next, we took cationic lipids, which is DDAB, with a helper lipid DOPE, in such as in the form of liposomes, to suspend them in aqueous solution. These lipids will help in the mucoadhesion of these nanoparticles into the nasal mucosa and also contribute to the immune response themselves. The triage and the lipids are combined together by charge-charge interactions to form cationic nanoparticles. And to these lipid triage, we added 3 acellular pertussis antigens, namely pertactin, pertussis toxin, and fibria. And these were added by 2 different methods of addition, such that in the first one, which is the LTA method, the antigens were actually placed on the outside of the lipid triage. And in the second one is the LAT method, in which the antigens were encapsulated inside the lipid triage system. We then tested these nanoparticles in vivo. We injected them into mice at 1 and 5 microgram total dose, followed by a booster dose at 4 weeks. And the antibodies associated with the antigens, each of these antigens, were estimated at 4 and 8 weeks. So first we looked at the physical characterization of these nanoparticles. When observing the sizes, we see how the lipids and the triage, when reacted together, they form condensed nanoparticles called the L-triage, which are smaller in size than the individual lipids and the triage. And then when the addition of the antigens into the L-triage affects their size such that the LTA is slightly bigger and the LAT is more bigger, which reflects the different packing of the antigens into these nanoparticles. And we also see a similar thing in the TEM images. So ultimately, the size of the nanoparticles that were administered into the animals were between 300 to 400 nanometers. In terms of the zeta potential, the triage is negatively charged or anionic individually, but with the addition of the cationic liposomes, All the nanoparticles were ultimately plus 50 millivolts in charge, as we had set to achieve them. Next, we move on to the in vivo results. And first, the response for the antigen pertactin. We see that the antigens alone did not generate any response of its own. But at 4 weeks, the response generated by the 5 microgram LTA was statistically higher for both IgA and the IgG2A antibodies as compared to the plain antigens. Another thing was that all the mice that responded to the vaccination at just 4 weeks for the lipid triage in the IgG2A. One more thing to note here is that the LTA produced a slightly better response as compared to the LAT formulation. Next, we moved on to the pertussis toxin responses. The antigens are stronger this time, and they produced their own antigen antibody response. However, we still observed statistically higher IgA and IgG2A for the lipid triage nanoparticles at both 4 weeks and 8 weeks as compared to the antigen alone group. And again, all mice in the lipid triage group responded to the vaccine after just 4 weeks and 1 dose of the vaccine. The third thing we observed was the secretory SIgA antibodies in the intranasal washes, and we continue to observe a similar trend here, that pertussis toxin produced a stronger response as compared to pertactin. And although it is not statistically significant, the average titers for the 5 microgram LTA vaccine were still 2.5 folds higher as compared to the unformulated antigens. And hence, the key messages that we take away from this research is that for respiratory infections, especially intranasal vaccines can prove very beneficial to achieve mucosal immunity at the local site of infection. And our LTA vaccines have helped to produce just that. We efficiently produce antibodies associated with mucosal immunity, and we also produce those associated for cellular immunity. And further, our lipid nanoparticle vaccines generated high immune response within just 4 weeks and 1 dose of the vaccine. An early response to the vaccine is essential since infants and neonates too young to receive primary immunization are more susceptible to pertussis infections. In terms of formulation design, we observed that antigens placed on the exterior of the lipid nanoparticles produced a better response, suggesting that it is important for the antigens to be easily presented to the mucosa to allow a sufficient and uniform antigenic effect. And hence we conclude cationic lipid-based vaccine nanoparticles formulated with a triple adjuvant are encouraging as a formulation for intranasally administered pertussis vaccines and also have the potential to be utilized for various other vaccine formulation designs. Thank you.
Excellent. Thank you very much, Noor. And I am pleased to open the floor for questions from the audience. You are all presently on mute, so to ask a question or join the discussion, you have to use your control panel to either raise your hand to speak or to submit a written question. So Hayden, are there any questions or hands at this time?
There are none at this time.
Great. Well, I'll take this chance to ask a question. Noor, could you speak to why generating an early response to the vaccine is necessary?
Thank you for the question, Leah. It is necessary because when adults are vaccinated, there are maternal antibodies present in the body, which are transferred over to the infants, and so infants cannot be vaccinated for pertussis until 2 months of age, and that is where they are most vulnerable and susceptible to these infections. And so, the earlier a response that we can produce to the vaccine, the better beneficial it will be for the infants. And that's why it is very important to generate an early response to that vaccine.
Great, thank you, Noor. And I believe I see a hand up for actually one of our other presenters, Michael Valek. So Mike, you can unmute yourself and ask your question.
Thank you, Leah. Great presentation. So I had a question about the intranasal delivery. So after you've administered the particles intranasally, where do they go? Do they go like further down the respiratory tract to the lungs, or do they stay in the upper respiratory tract? Do you have a sense of that?
Yes, from the intranasal delivery, we aim for them to taken up into the mucosal through the mucosal route directly into the systemic circulation, and also we expect some of them to transfer to the lymph nodes where they are presented to the antigen presenting cells, and so through the serum and through the lymph nodes, we expect them to then produce the cellular systemic immunity and also the mucosal immunity.
Okay,
Excellent.
thank you.
Great. Thank you, Noor, for your answer, and Michael for your question. Hayden, are there any other hands or questions at this time?
It does not look like it.
Great, thank you. Well, Noor, I have another question. I think you mentioned that there were 3 antigens used for the vaccine formulation, but the results look like there were only 2 antigens. Could you speak to this?
Yes. We added 3 antigens, but we found that the third antigen, Fimbriae, did not produce a very sufficient antigenic response. And so we decided, even though we observed and estimated the antibody response, I decided to exclude this from this presentation.
Great, thank you.